Climate change is one of the most pressing issues of our time, and carbon dioxide emissions are at the heart of the problem. Over the past century, human activities have dramatically increased atmospheric CO2 levels, leading to global warming, rising sea levels, and extreme weather events. To combat these changes, scientists and engineers have developed various methods to capture and store carbon dioxide, a process known as carbon sequestration. This video will explore the latest advancements in CO2 sequestration, why it's essential for our planet's future, and how it fits into the broader fight against climate change. Let's begin by understanding the basics and the urgent need for effective solutions. Since the mid-1800s, atmospheric CO2 concentrations have risen from 280 parts per million to over 400 ppm. This increase has caused the Earth's average temperature to rise by nearly 1 degree C, resulting in significant environmental impacts such as melting glaciers and higher sea levels. International organizations like the IPCC and the European Union have set ambitious targets to keep global temperature rise below 2 degrees C by 2100. Achieving these goals requires drastic reductions in greenhouse gas emissions, especially from power plants and heavy industries, which are among the largest CO2 emitters worldwide. Power plants, especially those burning coal, oil, and gas, are responsible for a significant portion of global CO2 emissions. The high carbon intensity of these sectors makes them prime targets for decarbonization. Carbon capture and storage (CCS) has emerged as a leading solution capable of reducing emissions by up to 20% by 2050. Without CCS, the cost of meeting climate targets could increase by 70%. Governments and organizations worldwide are investing in CCS technologies to help achieve emission reduction goals and transition to a low-carbon future. Carbon capture and storage, or CCS, is a process that captures CO2 emissions from sources like power plants and factories, then transports and stores them underground or in other secure locations. The goal is to prevent CO2 from entering the atmosphere, thereby reducing its impact on global warming. CCS involves several steps: capturing CO2, compressing it, transporting it, often via pipelines, and finally injecting it deep underground into geological formations where it can be safely contained for centuries or longer. Final and most critical stage of the CCS process is the long-term storage of captured CO2. This is typically achieved by injecting CO2 into deep underground reservoirs, such as saline aquifers, depleted oil and gas fields, or other geological formations. In some cases, CO2 can also be stored in the ocean or converted into stable minerals through chemical reactions. Each storage method has its own advantages, challenges, and environmental considerations, which we'll explore in detail throughout this video. Choosing the right site for CO2 storage is crucial for safety, effectiveness, and public acceptance. Scientists must carefully evaluate geological formations to ensure they can securely contain CO2 for hundreds or even thousands of years. Factors like rock permeability, caprock integrity, and the absence of faults or fractures are all considered. Additionally, monitoring and verification systems are put in place to track CO2 movement and detect any potential leaks, ensuring long-term containment and environmental protection. Among all sequestration methods, underground geological storage is widely regarded as the most feasible and scalable. This approach leverages natural rock formations deep below the Earth's surface to trap CO2. Compared to oceanic or mineral storage, geological storage offers better economic viability, easier site accessibility, and higher security against CO2 leakage. It's already being used in several large-scale projects worldwide, making it a cornerstone of current and future climate strategies. Deep saline aquifers are underground rock formations filled with salty water. They offer enormous storage capacity for CO2 and are found in many regions around the world. When CO2 is injected into these aquifers, it displaces the brine and interacts with minerals in the rock, sometimes forming new compounds. While saline aquifers are promising, challenges remain, such as the need for suitable injection infrastructure and careful site characterization to prevent leaks and ensure long-term stability. Once injected into underground formations, CO2 can be trapped through several mechanisms. These include structural or stratigraphic trapping, where CO2 is held beneath impermeable rock layers; residual trapping, where CO2 is immobilized in tiny rock pores; solubility trapping, where CO2 dissolves in brine; and mineral trapping, where CO2 reacts with minerals to form stable carbonates. Each mechanism contributes to the long-term security of stored CO2, reducing the risk of leakage. Another popular option for CO2 storage is using depleted oil and gas reservoirs. These formations have already proven their ability to trap fluids for millions of years, making them reliable candidates for CO2 sequestration. Existing infrastructure such as wells and pipelines can often be repurposed for CO2 injection, reducing costs. Additionally, injecting CO2 into these reservoirs can enhance oil recovery, providing an economic incentive for operators. Enhanced oil recovery, or EOR, is a process where CO2 is injected into oil fields to increase the amount of oil that can be extracted. This technique not only boosts oil production but also allows for the permanent storage of CO2 underground. EOR projects have been widely implemented, especially in the United States, and have demonstrated the dual benefits of increased energy output and reduced greenhouse gas emissions. CO2 captured from industrial sources often contains impurities like sulfur oxides, nitrogen oxides, and trace hydrocarbons. These contaminants can cause corrosion in pipelines and injection wells, affect storage capacity, and even pose environmental risks. Therefore, it's essential to purify CO2 streams before injection and to monitor the composition throughout the storage process. Regulatory standards help ensure safety and effectiveness in all CCS operations. While EOR offers economic and environmental benefits, it also raises concerns. The process can produce large volumes of wastewater containing heavy metals and radioactive substances. Without proper management, these byproducts can contaminate drinking water sources. Strict regulations and advanced waste treatment technologies are necessary to minimize environmental risks and ensure the sustainability of EOR projects. Mineral coal seams offer another opportunity for CO2 storage. These formations can absorb large amounts of CO2, displacing methane in the process. This not only sequesters CO2 but also enhances coal bed methane (CBM) production, providing an additional energy resource. However, the economic viability of this method depends on gas prices and the technical challenges of injecting CO2 into coal seams. Saltic rocks, found in both continental and oceanic regions, have emerged as promising candidates for CO2 storage. Their unique mineral composition allows for rapid chemical reactions with CO2, forming stable carbonates. Pilot projects such as the CarbFix initiative in Iceland have demonstrated the potential for fast and permanent CO2 sequestration in basalt formations. However, challenges like variable permeability and the risk of fractures require further research. Deep sea and permafrost regions can form CO2 hydrates, crystalline structures where CO2 is trapped within water molecules. These hydrates are stable under high pressure and low temperature, making them a potential storage option in specific environments. While the technology is still in early stages, research continues into the feasibility and safety of storing CO2 as hydrates, especially in methane-rich sediments where CO2 can replace methane. Enhanced geothermal systems (EGS) use CO2 as a working fluid to extract heat from deep underground rocks. This approach not only generates renewable energy but also provides a means to store CO2. The unique properties of CO2, such as low viscosity and high heat capacity, make it an efficient medium for geothermal energy extraction. However, EGS is still in the experimental phase, with ongoing research into its technical and economic viability. Mineral carbonation is a process where CO2 reacts with natural minerals, such as magnesium or calcium silicates, to form stable carbonates. This can occur naturally underground or be engineered above ground in industrial facilities. While mineral carbonation offers permanent storage, it requires significant energy and resources, making it more expensive than other methods. Research is ongoing to improve efficiency and reduce costs. There are two main approaches to mineral carbonation: in situ and ex situ. In situ carbonation involves injecting CO2 directly into underground rock formations where it reacts naturally over time. Ex situ carbonation takes place above ground, where minerals are mined, processed, and reacted with CO2 in controlled environments. Each method has its own benefits and challenges, particularly regarding energy use, environmental impact, and scalability. While mineral carbonation offers a permanent solution for CO2 storage, it can have significant environmental impacts. Large-scale mining and processing of minerals can alter landscapes and generate waste. Some mineral deposits may contain harmful substances like asbestos, requiring careful management and monitoring. Future research aims to minimize these impacts and develop safer, more sustainable carbonation processes. Another method for CO2 sequestration involves injecting CO2 into the deep ocean. The ocean covers 70% of the Earth's surface and has absorbed about a third of human-made CO2 emissions. Injecting CO2 at depth below 1,000 meters can keep it isolated from the atmosphere for centuries. However, this approach raises concerns about ocean acidification and impacts on marine life, making it a controversial and heavily regulated option. There are two main techniques for ocean storage: dissolution and lake type. In dissolution storage, CO2 is injected into the water column where it dissolves and disperses. In lake type storage, CO2 is deposited on the ocean floor, forming a dense layer that slowly dissolves over time. Both methods rely on the cold, high-pressure environment of the deep ocean to keep CO2 contained, but each has unique environmental and technical challenges. Storing CO2 in the ocean is not without risks. Localized acidification can harm marine ecosystems, especially organisms sensitive to pH changes. There are also legal and ethical questions about whether CO2 should be classified as industrial waste and whether it's permissible to inject it into the ocean. International agreements, such as the London Convention, strictly regulate ocean storage, and ongoing research aims to better understand the long-term impact. Effectiveness of ocean storage depends on factors like injection depth, residence time, and CO2 concentration. Deeper injections keep CO2 isolated longer, but modeling studies show that some leakage back to the atmosphere is inevitable over centuries. Researchers use advanced ocean circulation models to predict CO2 movement and assess the environmental impact, helping to guide future policy and technology development. To advance ocean storage, researchers are focusing on improving technology for deep-sea operations, developing better monitoring systems, and understanding the ecological impacts of CO2 injection. Large-scale experiments and dedicated research centers are essential for testing new equipment and methodologies. The goal is to maximize storage efficiency while minimizing environmental risks and costs. Each CO2 sequestration method, geological, mineral, and ocean storage, has its own strengths and limitations. Geological storage is currently the most practical and widely used, offering high capacity and security. Mineral carbonation provides permanent storage but is energy-intensive and costly. Ocean storage offers vast capacity but faces environmental and regulatory hurdles. The choice of method depends on local geology, economics, and societal acceptance. One of the biggest challenges in CO2 sequestration is accurately estimating storage capacity. Geological formations are complex, and predicting how much CO2 they can hold safely requires detailed analysis of rock properties, fluid dynamics, and chemical reactions. Uncertainties in these estimates can affect project planning, costs, and long-term security. Ongoing research aims to improve modeling techniques and reduce these uncertainties. Ensuring the safety and effectiveness of CO2 storage requires robust monitoring and verification systems. These systems use sensors, seismic surveys, and chemical tracers to track CO2 movement underground or in the ocean. Early detection of leaks or unexpected behavior allows for rapid response and mitigation. Transparent monitoring also builds public trust and supports regulatory compliance. Success of CO2 sequestration projects depends not only on technology, but also on public acceptance and supportive policies. Communities must be engaged early in the planning process, and concerns about safety, environmental impact, and land use must be addressed transparently. Governments play a key role in setting regulations, providing incentives, and ensuring that projects meet high standards for safety and sustainability. Cost is a major factor in the deployment of CO2 sequestration technologies. Geological storage is generally the most cost-effective, especially when existing infrastructure can be reused. Mineral carbonation and ocean storage are more expensive due to higher energy and operational requirements. Financial incentives, carbon pricing, and government support can help make these technologies more competitive and accelerate their adoption. Advancements in materials science, engineering, and data analytics are driving improvements in CO2 sequestration. New drilling techniques, better sensors, and advanced modeling software are making it easier to identify suitable storage sites, monitor CO2 movement, and optimize injection strategies. These innovations are helping to reduce costs, increase safety, and expand the range of viable storage options. Large-scale CCS projects are already underway in countries like the United States, Canada, Norway, and Australia. These projects demonstrate the technical feasibility and economic potential of CO2 sequestration. They also provide valuable data and experience that can inform future projects and policy development. International collaboration is essential for sharing best practices and accelerating global progress. Weyburn Project in Canada is a leading example of CO2 storage combined with enhanced oil recovery. Since its inception, millions of tons of CO2 have been safely injected underground, extending the life of the oil field and providing valuable insights into long-term storage behavior. Continuous monitoring and research at the site have helped improve understanding of CO2 rock interactions and storage security. Arbfix, a pioneering project in Iceland, injects CO2 into basaltic rocks, where it rapidly reacts to form stable carbonates. This process has demonstrated that mineral carbonation can occur much faster than previously thought, offering a promising pathway for permanent CO2 sequestration. The project's success has inspired similar initiatives in other volcanic regions worldwide. Effective policies and regulations are essential for the safe and widespread adoption of CO2 sequestration. Governments must set clear standards for site selection, monitoring, and liability. International agreements, such as the London Convention and regional protocols, play a key role in governing ocean storage and cross-border projects. Ongoing policy development ensures that CCS technologies are deployed responsibly and sustainably. Comprehensive life cycle assessment, LCA, is necessary to evaluate the true environmental impact of CCS technologies. This includes accounting for energy use, material inputs, and potential emissions throughout the capture, transport, and storage process. LCAs help identify areas for improvement and ensure that CCS delivers genuine climate benefits without unintended consequences. Despite significant progress, uncertainties remain in CO2 sequestration, particularly regarding long-term storage security, site-specific risks, and the potential for induced seismicity. Ongoing research, field trials, and improved modeling are essential for addressing these uncertainties and building confidence in CCS as a reliable climate solution. Public engagement is vital for the success of CCS projects. Transparent communication, community involvement, and education help address concerns and build support. Successful projects often involve local stakeholders from the outset, ensuring that their voices are heard and their interests protected. Building trust is key to achieving widespread adoption of CO2 sequestration technologies. Sustainability is at the core of CO2 sequestration efforts. Future research aims to make storage methods more efficient, less costly, and environmentally friendly. Integrating CCS with renewable energy, improving mineral carbonation, and developing new monitoring technologies are just a few of the directions being explored. The ultimate goal is to create a portfolio of solutions that can be tailored to different regions and industries. Carbon capture and storage is a critical component of the global strategy to combat climate change. Alongside renewable energy, energy efficiency, and behavioral changes, CCS provides a pathway to achieve deep emission reductions in sectors that are otherwise difficult to decarbonize. Its role will only grow as countries strive to meet their climate commitments and transition to net zero emissions. CCS works best as part of a comprehensive climate strategy. By integrating it with renewable energy, energy storage, and demand-side management, we can create resilient and flexible energy systems. Combining CCS with bioenergy BECCS even allows for negative emissions, removing CO2 from the atmosphere and storing it permanently underground. Looking ahead, the continued development and deployment of CO2 sequestration technologies will be essential for meeting global climate targets. Collaboration between governments, industry, and the scientific community is crucial for overcoming technical, economic, and social barriers. With sustained investment and innovation, CCS can play a transformative role in building a sustainable, low-carbon future. Sum up, CO2 sequestration encompasses a range of technologies and approaches, each with unique advantages and challenges. Geological storage is currently the most practical, while mineral and ocean storage offer additional options for the future. Accurate site selection, robust monitoring, public engagement, and supportive policies are all essential for success. As research continues, these methods will become safer, more efficient, and more widely adopted. Ongoing research is vital for addressing remaining uncertainties and improving the performance of CO2 sequestration technologies. Field trials, laboratory experiments, and advanced modeling all contribute to a deeper understanding of storage mechanisms and risks. By investing in research and development, we can unlock new solutions and ensure that CO2 sequestration remains a cornerstone of climate action. Carbon dioxide sequestration is more than just a technical solution, it's a vital part of our collective effort to secure a stable and sustainable climate for future generations. By combining science, technology, policy, and public engagement, we can rise to the challenge of climate change. The journey is ongoing, but with determination and innovation, a low-carbon future is within reach.